Hello everyone and welcome to Euclid Book 1 Proposition 10. This is another construction proposition very similar to Proposition 9, only instead of bisecting an angle we are bisecting a line. So we'll just jump straight in here. Euclid says to bisect a given finite straight line. So let AB be the given finite straight line. So give yourself a finite straight line AB, there it is. Thus it is required to bisect the finite straight line AB. Let the equilateral triangle ABC be constructed on it, which we can do by Book 1 Prop 1. So remember, you do that by drawing two circles. One starts at A and goes out to B. One starts in B and goes out to A. On either side, I'll do above, where they intersect, call that C. There we go. And finish connecting your lines there, so C to A and C to B. And then we will have constructed a nice little equilateral triangle here. And then Euclid says, and let the angle ACB be bisected by the straight line CD, which we can do by Proposition 9. So remember the way we did this on Proposition 9 was you had these arbitrary lines here, and you picked some point at random on one of them, and then you drew a circle to pick another point the same distance way over here, and that allowed you to construct a new equilateral triangle and bisect the angle. But we don't really need to do that here because since this is already an equilateral triangle, we already know that the CA distance is equal to the CB distance. So all we need to do is construct another equilateral triangle on the other side, which, you know, we've already drawn the circles for it. So you, just mark the intersection point down here. I'm going to change its name in a second here, but go ahead and mark the intersection point down there and connect these to make a second equilateral triangle down below. And I'm going to change the name of that for reasons that will become obvious in a second here, just to match Newton, or sorry, Euclid. I'm mainly a physicist, sorry. Going to change this to anything else, call this Z, whatever. All right, and then, in my case, going to reconnect this line CZ. And then where that actually intersects line AB, I'm going to call that D to match Euclid's, notation there. There we go. So we're done now. So we know that this line, we know for sure that this line CZ definitely bisects the angle ACB because we proved that in Proposition 9. In other words, this little angle right here is definitely equal to this little angle right here. Okay. Euclid says, hey, it's also true that the AD distance equals the AB distance, and he's going to argue that from his side angle side proof. So if we continue, which is Proposition 4. So if we continue, let Euclid do the reasoning here. Euclid says, I say that the straight line AB has been bisected at the point D. For since AC is equal to CB, so since AC is equal to CB, and CD is common, so in other words, he's looking at this triangle right here, okay, and this triangle right here, and he's saying, hey, this side is equal to this side, and this angle, or sorry, and this side is common to both those triangles, right? Yes, it is. Then he continues, the two sides, AC and CD, are equal to the two sides, BC and CD, respectively, what we just said, and the angle ACD is equal to the angle BCD. So in other words, this little angle right here is equal to this little angle right here. Then he says, therefore, the base AD is equal to the base BD. So by Proposition 4, side, right, side, angle, side is equal to side, angle, side. So the remaining sides must be equal as well, and the remaining sides are AD and BD. So Euclid has proven that AD is equal to BD, which means that AB has been bisected. So Euclid finishes, therefore, the given finite straight line AB has been bisected at D, QEF.